Hey, sup? What if you could connect to your RDS Aurora database without ever storing or passing around a single static password? In this video, I'm going to show you how you can leverage IAM authentication to make that happen, so you can scale your applications securely and say goodbye to hard-coded credentials. Hi, if you're new around here, my name is Ryan. I'm an AWS Certified Solutions Architect and Developer, and my goal is to teach you modern serverless system design using AWS. Let's jump in. All right, so let's talk a little bit about why you would want to use IAM authentication for your database rather than just a username and password. Well, the first reason is that usernames and passwords can be easily leaked. They can also be shared improperly across insecure channels. They can be committed to source and or left in a repository and forgotten about. And finally, in order to remain secure, they must be rotated regularly, which can be a pain. On the other hand, IAM Auth allows you to easily create new users for your database. Because we manage permissions in IAM, it allows us to centralize our user management and easily rotate or revoke credentials. As our application scales, it allows us to not have to manage multiple sets of credentials and passwords. Because instead of a password, we will authenticate to the database using tokens, which eliminates one of the biggest security risks in modern applications. And because authentication happens through IAM, we gain more comprehensive logging and simplified auditing through CloudTrail. Today, I'm going to show you how to leverage IAM authentication with an RDS Aurora Database and Secrets Manager. This setup will help you manage your root user credentials securely, create new database users on demand, and authenticate to the database without using and sharing passwords. We're going to create a VPC, an Aurora database within that VPC, and a Lambda function within that VPC, and we're going to manage and deploy all of this architecture using the AWS CDK. So let's dive right in and start building. All right, so let's go ahead and init our CDK project. We'll just make a directory called CDK RDS IAM. We'll CD into that directory, and we'll CDK init app-l TypeScript. All right, perfect. So let's open this up here. First thing we'll do is we'll hop into bin and we'll clean this up a little bit. We'll go ahead and explicitly pass in our env with our account and our region. All right, next thing, let's go ahead and jump into our package.json, and we'll go ahead and add all of the packages that we're going to need for the Lambda function. We're going to add the Secrets Manager and the RDS Signer from the AWS SDK, and we'll also include the PG package. This is going to allow us to communicate with the database. And we'll also go ahead and add the PG types to our dev dependencies. We'll npm I to install all those dependencies. All right, perfect. So let's make a folder for our layers. Now, in order for our Lambda function to run, we're going to need the PG package. I included it in the root package.json. This just makes it so that it doesn't give us errors when we try to use it when we're actually writing our Lambda function code in the repository. However, when we actually go to deploy the Lambda function, we will not have the PG package available at runtime unless we either package it with the Lambda function or include it as a Lambda layer. Personally, I like to use a Lambda layer because a lot of times you're going to have multiple functions that reuse all the same packages. So let's go ahead and create that Lambda layer folder right now. So in the root of our project, we'll make a directory called Lambda layers. Inside that folder, we'll create a folder called pg-layer. And then inside the pg-layer, we'll create a folder called node.js. The important thing to note about Lambda layers here is that it doesn't actually matter which nested folder structure you use. You just have to make sure that the very lowest folder that contains the package.json that you're going to use to package up your layer is called node.js. So we'll cd into that node.js folder and we'll do an npm init. All right, we can just enter through all of these because none of this really matters. Now inside that package.json, we can go ahead and open it up, and the only thing we're going to include is our dependencies of the PG package. Great, so now that we're in that folder and we have that one package, let's just do an npm install here. And now you can see it creates a nested node modules inside of the node.js folder. Everything in this node.js folder will be packaged up by the CDK and uploaded so that we can use it as a layer that will make the PG package available for our Lambda at runtime. Next, let's define our TS config that we're going to use to build our Lambda function from TypeScript into JavaScript. We'll update the module to nodenext and the lib to esnext, just to ensure that we're using the modern versions of TS and JS. Next, we'll just include our outdir to just be the dist folder. This will make sure that anytime we compile all of our TypeScript into JavaScript, it puts it into this dist folder rather than just putting it into the subfolders in which all of the TypeScript files will exist. Just keeps the repo a little bit cleaner. Finally, we're then going to tell TypeScript to ignore the dist folder. All right, perfect. So let's go ahead and create our Lambda function folder now. We'll cd back out to the root, and we'll make a folder called services. For this particular Lambda function, I'm putting it in the services folder because we're actually going to have it be triggered by a separate function trigger that will run every time we update our CDK stack. This will make more sense in a little bit. Let's create our Lambda function file. We'll do touch services index.ts. So before we build our Lambda function, let's go over a little bit about what this Lambda function is supposed to do. I mentioned that we're going to create a Lambda trigger. This trigger is going to trigger the Lambda function every single time our CDK stack updates. So what this function is going to do is it's going to connect to our RDS database using our root user credentials that we'll define in our stack in a minute. Once it connects, it will then create our new IAM enabled user, grant it the IAM permissions that it needs, and then close the connection. Next, we will initiate a second database connection that attempts to connect to the database using our newly created IAM user and a token, just to ensure that our new IAM user is indeed able to connect to the database. So let's go ahead and start building this now. First, we'll import a couple things from those packages that we added in our root package JSON. The root database credentials are going to be stored in Secrets Manager, so we're going to need to fetch those first. Then we're going to import the RDS signer. The RDS signer is what's going to allow us to generate a token to then use to log in with our newly created IAM user. Finally, of course, we're going to need the client object from PG. That's going to allow us to actually create and connect to our database client, whether we're doing that with our root user credentials or with our IAM user and token. Next, from our env variables, we're going to take our IAM user, the ARN of our secret that we're going to look up, and the region. When we build our stack here in a second, we're going to pass all of these values in as environment variables into our Lambda function. Next, we'll create an interface that represents our DB credentials. In our two database connections, the two things that will change will be the username and the password, but the structure will remain the same for both connections. We'll define our first function that is going to be responsible for going to Secrets Manager and fetching our root database credentials. When we create this Secrets Manager object in the CDK, is going to contain not just the root username and the password, but the host, the port, and the database name, allowing us to get everything that we need to connect from this one call. First, we'll do a quick check to ensure that the secret ARN got passed in appropriately. If not, it'll just throw an error. Next, we'll create our Secrets Manager client and our getSecretValue command, which will pass in our secret ID as the secret ARN. We'll then send the secrets client the getSecretValue command, and then we'll check to make sure that the secret exists. Next, assuming that our secret exists, we're going to parse it and store it as an object. And then from this function, we'll return everything that we need to connect to the database. The next function that we're going to create is going to return our RDS client, which is going to allow us to then connect to the database and run SQL commands. This client's going to take in the same parameters regardless of whether we're using the username and password or we're using our IAM user and token. So we'll return a new client that has the database name, the host, the password or the token, the port, and the database user. One thing that I'll note here in the client configuration is that I set reject unauthorized to false for the SSL settings. In a production environment, you would never want to set this to false. You'd always want to enforce SSL. Setting this to false does create a security vulnerability. However, for the purposes of testing or in a dev environment, it's probably fine because everything that we're going to be doing exists within our own VPC. It's a little bit more to set up, and for the sake of brevity in this tutorial, I'll include some documentation down in the description if you want to set it up yourself. Next, we're going to set up our function that's actually going to create our IAM user once we're able to log in with our root user credentials. The first thing we'll do is we'll create a new RDS client by passing in all of our credentials. All right, let's set up a try, catch, and finally block. We'll attempt to connect to our database with our credentials, and then we'll send a console.log if it was successful. Next, we'll define our SQL statement that we're actually going to run to create our IAM user. The first thing we're going to do is we're going to check to make sure that the user doesn't exist. If the user doesn't exist, we're going to go ahead and create the user with the IAM username that we pass in. Next, and this is the most important line of this SQL statement, and we're going to grant the RDS_IAM permissions to our IAM user. This is what's actually going to enable IAM to work for this user and allow us to generate tokens. We're going to also have to assign an additional IAM permission when we create our stack, but I'll show you how to do that here in a second. Next, we're going to grant basically all permissions to all tables in the public schema for this IAM user. This is good for a couple reasons, because you can actually scope this user to only have access to the tables that you want it to. This is another great reason why you would want to use IAM users, because it's a lot more secure and you can use application-specific users for your database to ensure that in case one of them ever got compromised, it would never be able to communicate with any tables that you didn't want it to. All right, so now we're going to take that SQL statement and we're actually going to query our database. And we'll do a quick console log here at the end just to ensure that everything got inserted correctly. In our error, we'll just make sure that if we have any errors along the process, it throws them. And finally, when it's all said and done, we'll actually end our connection to our database. And this will end our first database call. Next, we're going to define our function that's actually going to attempt to connect to the database with our newly created IAM user. So this will be our second database connection. So the first thing that's different here is we're going to first have to create a signer configuration to then pass into our RDS signer that will allow us to generate our token. So we'll pass in our host, our port, our region, and the name of our DB IAM user. We'll then create our signer by passing in that signer config, and then we will generate our token with the getAuthToken method, and then we'll just send a quick console log to make sure that we were able to generate this token successfully. Now everything will follow basically the exact same process from here on out. We're just going to create our new RDS client, and instead of passing in the password, we're just going to pass in our token. We'll set up another try, catch, and finally block. We'll first try to connect to the database using our token and IAM user, and we'll send a console.log if it's successful. Just to further validate that our IAM user is actually able to do things in the database, we're going to create an SQL statement to just list all the database tables. We'll then query the client with that SQL statement, and we'll just print out all the tables. Again, if there's a problem, we'll just log the error. And finally, we'll end our second database connection. All right, finally, let's define our Lambda handler that will actually define the function that will be called anytime this function is triggered. We'll export a const of handler. And then the first thing we're going to do is we're going to attempt to get our root database credentials from Secrets Manager. Next, we'll call our database function that connects as our root user and then creates our IAM user and grants it the correct privileges. If that's successful, we'll just log that it was successful and that we were able to connect using our root username and password. Finally, when that connection closes, we will then attempt to initiate our second connection to the database as our IAM user using a token. And finally, if everything was successful, we'll just return a 200 status code from our function. And that wraps up the Lambda. Let's go ahead and hop in and actually start building our CDK stack. All right, so let's go ahead and open up our lib, and then we'll open up our actual stack definition here. All right, so we'll clean this up here, get rid of the comments. We're going to destructure stack and stack props from the CDK lib, and we'll get rid of SQS. All right, so we'll first define our static variables that we're going to need for the stack. We'll define our database name. We'll just call it main.db. We'll define the name of our DB root user, and then we'll define the name of our DB IAM user. All right, let's start building our actual AWS infrastructure that we're going to need. First, you should go down and like the video if you've made it this far, and then let me know down in the comments if there's any other videos that you want to see me make on this channel. All right, before we create our database and our Lambda function, we're first going to need to define a VPC in which both of them can live. Our VPC is going to house both our RDS database and our Lambda function, allowing them to easily communicate with each other, but stay in a private network so that they cannot be accessed from the outside. So we'll do a const VPC is equal to a new VPC imported from EC2. We'll pass in this, we'll pass in our logical resource name. And then into our VPC props, we'll set our max availability zones to 2. We'll then define our subnet configuration set to an array that's going to take in 2 objects. The first property of the first object will just be our CIDR mask. We'll set it to 24. We'll name the subnet public. And of course, we'll set our subnet type then equal to subnet type dot public. Let's go ahead and duplicate that. And then we'll make the second one our private subnets. We'll set that subnet type to private with egress. This will allow anything that's in this subnet to send traffic out to the internet, but it will not accept any traffic incoming from the internet. Next, we'll create this security group that our database is going to use. We'll set DB security group is equal to a new security group imported from EC2. We'll pass in this, the logical resource name of Aurora security group. And then into our security group props, we're going to pass in the VPC, and then we'll set allow outbound to true. And this will allow our egress to function if we decide to use it. All right, we're basically going to repeat that with our Lambda security group. And then we just need to make sure that our Lambda security group is actually allowed to connect to our database security group. So we'll take our DB security group dot add ingress rule. This will allow ingress from anything that we pass in. In this case, we're just going to pass in our Lambda security group. We'll then say which port we're going to allow ingress on. In this case, it's going to be 5432, which is the default port for PostgreSQL. So we'll import port from ec2.tcp, and then into that, we will pass the port number of 5432. Finally, we'll add an optional description that says allow Lambda access. Next, let's go ahead and define our Secrets Manager object that's going to store all of our database connection credentials. So we'll do const credentials. We're going to set credentials equal to a new credentials. This credentials object is imported from the RDS library dot from generated secret, where we're then going to pass in the DB root user that we defined at the very beginning of the stack. This is going to create a Secrets Manager object that contains not just the user and the password, but also the host name, the database name, and the port, everything that we need to connect to the database. All right, let's create the biggest part of this stack, which is going to be our Aurora database cluster. We'll do a const cluster is equal to a new database database cluster imported from RDS. And then of course into this, we're going to pass a number of different settings. The first thing we're going to define is our database engine. We'll set engine to a database cluster engine dot Aurora Postgres, which will then pass in an object with a single value, where we will set the version to Aurora Postgres engine version dot version 16.6. Next, of course, we're going to have to pass in the VPC that we defined. This is where our database is actually going to live. Next, we're going to define which VPC subnets we actually want the database to live in. We'll just set this equal to an object, where we'll then define the subnet type to be that subnet type object dot private with egress. This will automatically on the back end just find all of our private with egress subnets that exist and put the database in each of those. Next, we'll define the database security groups. This is set to an array, but it's just going to have a single value, and that's going to be set to the database security group that we created earlier. Next, we're going to set our default database name. This is just going to be the database that gets created as soon as the cluster gets created. And we'll set that equal to the DB name that we defined at the beginning of the stack. For removal policy, I'm going to set this to removal policy.destroy, because Aurora Postgres databases, especially ones that are going to use serverless readers and writers, like we'll define here in a second, are very expensive just sitting around. They'll cost pretty much at a minimum about $200 a month. So you want to make sure that when you're done spinning this up, if you don't need it, make sure you take it down, otherwise it's going to cost you. So let's define our readers and our writers. The nice thing about Aurora is that it actually doesn't just create a single database, but it creates a database cluster. What this means is that you've actually got a single instance that you can write to, but you can define multiple reader instances. So in the chance that you're making a lot of calls that are just reading from the database, you can actually distribute that traffic over a bunch of different reader nodes, so it doesn't overload your primary writer node. And because the cluster instances that we're going to define for our readers and our writers are serverless, this means that they also have a lot of really nice auto-scaling functionality that's just built into the database. So let's define those right now. First, we'll define our writer. We'll set that equal to a cluster instance dot serverless v2. You do have the option for using provision database instances here. Provision database instances are going to be a lot cheaper when they're just sitting idly, but the downside of them is that you have to then monitor them and make sure you know when you need to scale them up and when you need to scale them down. By choosing serverless and actually serverless v2, Aurora takes care of all of that stuff on the back end for us. So we'll pass in a name for our serverless v2 instance and we'll just call it writer serverless. Next, we'll define our readers. Now readers, because we can have multiple of them, is actually going to be set to an array. But for the purposes of this tutorial, we're just going to create a single reader. Again, this is going to be a cluster instance, serverless v2, where we will pass in the name of reader serverless, but we're going to pass in one optional property here into an object. And the single property that this object is going to have is scale with writer. And we're going to set that to true. One thing about Aurora is really smooth failover. So in the instance that our writer node goes down, it can actually seamlessly fail over to one of our reader instances. And then it will promote that reader instance to be the new writer instance. However, in order for that to happen, we need to make sure that at least one of our readers has this scale with writer set. This ensures that we at least have one reader node that matches the size of our writer node and will minimize our downtime or service interruption in the event of that failover happening, because this reader node will be the one that's picked to replace the writer node. All right, so let's define a couple more things. Because we've selected serverless, that means that we've got auto scaling built in under the hood. In order to control that auto scaling functionality, we want to make sure that we set a min value and a max value to ensure that our database stays between those two numbers. We control that with our serverless v2 min capacity and max capacity. Now, what is actually being set here? Well, these numbers correspond to Aurora capacity units, and one ACU corresponds to about 2 gigabytes of memory. So we're going to set this to 0.5. This corresponds to roughly about 1 gigabyte of memory, and this will be the smallest size that our serverless instances can scale down to in times of low traffic. And we'll set our max capacity to be 2, which is going to be equal to about 4 gigabytes of memory. And finally, the most important property to set on our database is going to be to set IAM authentication to true. Of course, this is going to allow us to use IAM authentication for the users of our database. All right, let's go ahead and create our Lambda layer. We'll set const pg layer is equal to a new layer version imported from Lambda. We'll pass in this, the logical resource name of pg layer. We'll tell it where to find the code for this layer, and that will be set to the code object imported from Lambda dot from asset, into which we are going to pass the directory where our Node.js folder is located. And of course, this is going to correspond to the root of your CDK project. We find that in lambda-layers/pg layer. Remember, this is just pointing to the folder that contains that folder that's called Node.js, that's going to have your package.json and your node modules containing your PG package. We'll set compatible runtimes equal to an array. We'll import runtime from Lambda, and we'll set it to Node.js 22. And then we'll just set a description saying that this layer contains the PG package. All right, let's actually define our Lambda function now. We'll set const Lambda function is equal to a new function imported from AWS Lambda. We'll pass in this plus the logical resource name of Aurora Lambda. We're going to set this runtime to the same runtime that we used for our Lambda layer, otherwise they won't be compatible. Once again, we're going to do code, and we're going to set that equal to code from asset. And we're going to tell it where the compiled JavaScript file is going to exist, not where the TypeScript file exists. We're going to set this to dist/services, of course, because anything that goes into the dist folder when we build it is going to maintain the same folder structure as the actual repo. And because we named our Lambda function file index, we're just going to do index.handler, because handler is the name of the exported Lambda function handler back in our TS code. Next, layers is just going to be equal to an array, and we're just going to pass in the PG layer that we created. We're going to pass in our VPC that we created earlier as well, because we need this Lambda function to exist within the VPC so it can communicate with our database. And we'll set security groups equal to another array where we'll pass in our Lambda security group. Finally, we're going to define an environment object because we're going to need a few values from the different resources that we've created here in the stack. The first thing we need is our DB IAM user we defined. Next, we're going to need the secret ARN of our database secret and our region where we're going to be creating our stack and our database. Next, we need to allow this Lambda function to actually read the secret in Secrets Manager. So we're going to do cluster.secret.grantRead, and we're just going to pass in our Lambda function. On the back end, this is going to generate the necessary IAM permissions in order for the Lambda function to be able to read from Secrets Manager. Next, we're going to define the permissions that will actually allow the Lambda function to connect to the database using our IAM user that we're going to create. We'll do Lambda function.add_to_role_policy. And in this, we're going to pass a new policy statement imported from IAM, where we'll then pass in an object. The first thing we're going to need to do is define the action that we're going to allow the Lambda function to execute. And that is RDS-DB::connect. And then we're going to allow the resources that we're going to allow that action to be performed on by the Lambda function. And we're going to pass in the ARN of the IAM user that will be created that we're going to allow the Lambda function to connect as. One important thing to note here is that as DB user, you're going to then pass in the cluster, and you're going to pass in the cluster resource identifier. This is different than the cluster identifier. They are two completely different values, and you need to make sure that you're passing in the cluster resource identifier. And then of course, we're going to pass in the IAM user that we're going to allow the Lambda function to connect to the database as. An important thing to note here is that this is just granting the Lambda function the ability to connect to the database, but any AWS service that you want to use, whether that's EC2 or EKS or anything else, as long as it has these permissions, it will be able to connect using that IAM user. And of course, you enable its security group to connect to the database security group. And next, we're going to set up the trigger that's actually going to trigger the Lambda function to execute. We'll do a new trigger, and it's going to be the trigger from the triggers library, not from the code pipeline library. We're then going to pass in this. We're going to pass in the logical resource name trigger on deploy. This is, of course, going to trigger the Lambda function every single time we deploy an update to our CDK stack. We're going to set first execute after equal to an array, and this is actually going to take in any construct that's defined within this stack. And of course, in this case, we want to make sure that the Lambda function does not trigger until our cluster has either finished creating or updating anytime we deploy. We'll of course set our handler to our Lambda function that we defined. We'll then set invocation type, and that will be invocation type imported from the triggers library .event. And then we'll set our timeout to just be a duration.minutes of 10. One thing I forgot on the Lambda function is we want to set the timeout value here to be a duration.seconds of at least 30. So a couple of things to mention about the trigger. On the first deployment of this stack, it's going to create our Lambda function, but it won't actually trigger it until the cluster finishes creating. And of course, on the first deployment of this stack, the cluster is what's going to take the longest to create, usually about 15 or so minutes for a cluster like we've defined here. And another thing that I'll note about the trigger, and this is something that we will probably see when we deploy the stack, but the trigger seems to have some exponential backoff built in. I've noticed that sometimes the trigger will actually trigger the function, and then the function will time out when trying to connect to the database. And if an error occurs, it will usually attempt to try the function 1 or 2 other times afterwards until it's able to successfully execute. And I'm not sure exactly why this is, but I'm just noting it here because it's something that I noticed while testing. All right, so that finishes the stack. We're going to go ahead and deploy the stack now, but first we need to build our Lambda function. So we'll just npm run build, which will of course compile our TypeScript Lambda function into JavaScript. And we can see that our dist folder now exists. And one thing that we'll do here too, in our git ignore, we will just make sure that it ignores our dist folder so it doesn't commit it to source. And we can see that the dist folder maintains the exact same folder structure as the root repository, and inside services we can find our Lambda function here. All right, and now that that's built, let's go ahead and deploy. We'll just do cdk deploy -- profile cloudmancer. Oh, we had an error here, and that is because our layer is in Lambda layers, not Lambda layer. All right, let's go ahead and try that again. And then we can see all the changes that are going to be made with this stack, including our IAM policies. We'll just go ahead and hit yes. And like I said before, this is going to take about 15 or so minutes to create this cluster. We can see here that it's creating our VPC and the related networking resources, our security groups, subnets, etc. All right, now it's creating our database cluster. Let's go ahead and hop into the console and see our stack. All right, here we can go over to CloudFormation and we can see that our stack's being created. All right, we can see that these are all being created. All right, so now that the VPC is complete, we can see that it's going ahead and creating our writer and reader for our Aurora cluster and our Lambda function as well. All right, we can go check out our function here. We can see it in the console, and then we can go over to monitor and view CloudWatch logs. And you can see here that the log group doesn't exist, and this is because the function was created but it has not executed yet, of course, because we are still waiting on our Aurora cluster to finish. All right, so it looks like that created just about everything. We're just waiting on the Aurora cluster to finish, so we'll be back in a few minutes. All right, perfect. So it looks like the stack finished. Let's go ahead and check out our Lambda function to see if it ran. You can just refresh the log page and we can see that our Lambda function executed. We can see here we connected as the root user, we created our IAM user, we then closed the connection, and we retrieved our IAM auth token, and then we were able to successfully connect to the DB as our IAM user and then see all of the different tables that exist in the database. So one other modification that we didn't do in this video, but something that you would probably want to set up, is that while you are able to connect to the database using your IAM user, you definitely would want to set up some sort of rotation schedule for your root user credential secret. And we can see here in the console that it did take almost 20 minutes to deploy that database cluster. And then finally, please do not forget this step, but make sure you destroy the stack when you're done, because it will be extremely expensive if you let this thing run behind the scenes and then forget about it. So this is just a little disclaimer here to remember to do this. So we'll hit yes. Okay, and we finished destroying. That about wraps up the video today. Please don't forget to like the video, and then just let me know down in the comments if there's any other videos that you want to see me make on this channel. Thank you for watching.